So this is the elusive further functions topic that we never quite got to cover during our 3 terms this year. So I want you to just work through these exercises over the holidays. There's a couple of things that are a real benefit to you in this exercise. So let's just sort of start with 7a, which is called more power functions. Okay, so recall a power function is one where you've got y equals x and we've got some sort of power in this spot here. Okay, so just a couple of reminders that an odd function is one where if you reflect it, okay, so when you reflect it in the y-axis, it's exactly the same as reflecting in the x-axis. Okay, it's also called having rotational symmetry 180 around the origin. So imagine this graph here. If I put a pin here and rotate it 180 degrees, you'll note that this bit here will end up down here. Okay, so it has rotational symmetry. So that's an odd function. An even function is such that if you reflect it in the y-axis, this thing here, it'll be the same as, well, doing nothing. And you can see here that this would be what's called an even function here, because if you reflect it in the y, it'll just result in exactly the same function. All right, so now let's explore some different power functions. So if we've got x to the power of negative 1 over n, where n is a positive integer. So it could be things like f of x equals x to the negative 1 over 2, say, for argument's sake. And so what I've drawn here is a couple of different versions of this. So basically, if n is odd, so if this condition is the case, then what you get is a kind of what I call hyperbolic graph. Okay, so one that looks a little bit like a rectangular hyperbola. Now the reason for that is let's just take one example. F of x equals x to the negative 1 on 3. That's the same as 1 over x to the 1/3, or 1 over the third root function. Okay, and recall that the third root function looks like this. Try again. All right, so what's going to happen here is this function here, 1 divided by 0 is undefined. Then we've got small values getting bigger and bigger and bigger. So 1 over a small value is really big. 1 over a big value is really small. So basically, when you do 1 over this graph here, it results in this graph here, so the hyperbola style graph. What about even? Well, very similar, but only this right-hand part. And the reason for that is, let's have a look at this one here. So when n is even, f of x equals 1 over root x. Now the reason why we only get this right hand side is that you can't find the square root of a negative number. So for values of x that are negative, this function here will be undefined. So we imagine the square root function like this, and then we do 1 over that, which will be that function there. So explain why there is a difference when n is even or odd. Basically, I'll summarize that as you cannot find the square root of a negative number. In math methods anyway, we say it's not real. If n is an odd positive integer, explain why f of x equals x to the negative. Okay, so basically we'll draw this graph here. Okay, and why would it be an odd function? Well, recall the definition of an odd function is that it has rotational symmetry 180 about the origin. Okay, so that is this would switch to there and this would switch to there if I rotate it 180 degrees about the origin. Okay. The other thing I could go on to explain is that f of negative x, so reflections in the y would be the same as reflections in the x-axis. Okay, so that's why it would be considered an odd function. Using the graphs of f of x equals, explain why it's neither odd nor even. Okay, so let's do that graph there. So that's this one. Now, it's not even, okay, because f of negative x would look like this. So that would be a reflection in the y, which would be this graph here, which is not the same as the original. Okay, so that would rule that out. So we're going to say not same as f of x. Or we could say that f of negative x not equal to f of x. Now, why isn't it odd? Well, we could again do rotational symmetry, 180 about the origin. That would produce this graph here. Okay, and so we can conclude that it's not the same after 180 degrees rotational symmetry. So we're going to say not same after 180 degree rotational symmetry about origin. So not even. Alright, use your calculator to help you sketch the following graph, state the maximal domain and corresponding range. Okay, so let's try to actually not use the calculator for it, and what we'll do is we'll rewrite it as 4 over x fourth rooted, take away 2. Okay, so what this is going to be is it's going to be the fourth root function, okay, which then becomes a hyperbola, and then it's going to be taken down 2 units. Okay, so the fourth root function is going to look like this. Then 4 over that is going to look like this, and then it's going to go down 2 units. Okay, so the resulting graph will be with an asymptote there. So let's draw that by putting an asymptote. So let's put that in there at y equals -2. And so it's going to go like this, which means we're going to get an x-intercept, which occurs when y is equal to 0. So we're going to go 0 equals 4 over the fourth root of x, take 2. 2 equals the 4 over the fourth root of x. Send that to there, send that to there, and we're going to get x to the quarter equals 2. And then what I'll do is fourth root both sides, or power 4 both sides rather. So x to the quarter to the 4 equals 2 to the 4. That gives me x equals 2 to the 4 is 16. Okay, so we've got an x-intercept of 16. Okay, so let's pop it maybe there. And hyperbolas are a bit hard to draw with this thing. Oh no. Well, that's going to have to do for the moment. That's pretty ordinary. But yeah, there's the graph of that one. Okay. This one, so we'll rewrite f of x as 2 over the third root of x plus 1. Okay, so recall that the third root function looks like this. 2 over it will look like this. And then this is just going to shift up 1 unit. So again, we're going to have an asymptote at y equals 1. So we're going to get this part, and we just need to get this part in a frame of reference down here. So we'll do the same thing as before. We'll go -1 equals 2 over x to the 1/3. -2 equals x to the 1/3 by transposition, power 3 that, power 3 that, that's -8 equals x. Okay, so we're down here somewhere, let's call that -8, and we'll draw this side of it, and then, because it's a rectangular hyperbola, we'll try to get that part looking a bit, I mean, that's completely dodgy, but I'm not going to fix that because I could have many goes at that and I'll get that wrong. We have one other asymptote that I need to put in, so that's this part here, and that is x equals 0. Okay, what about this one here when p and q are positive integers? Okay, well, there's a way to kind of work these ones out. I didn't state the maximal domain of those other ones. I think I was supposed to do that. State the maximal domain and the corresponding range. So we're going to say that x is an element of real positives, and y is an element of the values from -2 to +infinity. Oh, my handwriting's shocking. Okay, this one here, it is x is an element of all reals not including 0. Y is an element of all reals not including 1. Yeah. Okay, so yeah, these particular graphs, it helps if you know how these problems work. So this is 8 to the power of 2/3. Now, how do you raise 8 to the power of 2/3? Well, what you do is you break this up. So I'm going to write it as 8 to the 1/3 to the 2. Okay, so one power raised to another power, multiply the powers and we get that. Now that's the third root of 8, which is 2 to the power of 2. Okay, and 2 to the 2 is 4. So 8 to the 2/3 is in fact 4. All right. So this one here, okay, we'll think about this. The maximal domain, if q is odd, okay. So what's going to happen is we can let's summarize this once we've actually done 2 examples, or we see how 2 examples work. So this is f of x equals x to the 2/3. So the way to think about this graph is it's f of x equals x to the 1/3 to the 2. Right? Now that's f of x equals the third root of x to the 2. Now what does the third root function look like? It looks like that. Now when we square that, what it's going to do is basically just make this part of it higher, and this part of it matches this part on the right hand side of 0, except it now becomes positive because a negative times a negative is a positive. So we're going to get this graph here, this type of graph, and I think they refer to that kind of feature as a cusp. All right, this one here, so let's summarize that. If q is odd, okay, the maximal domain will be the set of all real numbers. Okay, so we can see that this function here is defined for all real numbers, because all of them, no matter what, if q is odd, okay, so if this denominator here, q is odd, they'll all look roughly like this. Okay, so if it's f of x equals x to the 2/5, okay, it'll form actually roughly the same shape. All right, what about this one here? So how does this graph work? Well, let's consider f of x equals x to the 1/2 to the 3. f of x equals root x to the 3. All right, so we've got the root x function here, and what they're going to do is then just cube all of these values, okay? So these large ones get bigger, and these smaller ones, when you cube them, actually get smaller. So we result in that graph there or that one there. Okay, so the domain, if Q is even, is all real positives union with 0. Okay, because we can produce that. Alright, so yeah, some funny looking graphs here, and from my mate who examines fairly heavily, says you will always have your calculator if these questions are ever asked. So do consider just going to your calc and graphing the function just to check it out.